Overview and definition: self-healing system. Self-healing term describes any application, service, or a system that can discover that it is not working correctly and, without any human intervention, make the necessary changes to restore itself to the normal or designed state. Because users of a product may find the cost of servicing it too expensive, some product developers are trying to build products that fix themselves. Self-healing is about making the system capable of making its decisions by continually checking and optimizing its state and automatically adapting to changing conditions. The goal is to make fault-tolerant and responsive system capable of responding to changes in demand and recuperation from failures. For example, some companies are working on an autonomic computing initiative that the company defines as providing products that are self-configuring, self-optimizing, and self-protecting, as well as self-healing. Fault model. Self-healing systems must have a fault model in terms of what injuries they are expected to be able to self-heal. Without a fault model, there is no way to assess whether a system can heal itself in situations of interest. The following are typical fault model characteristics that seem relevant. Fault duration. Faults can be permanent, intermittent, or transient. Since it is widely believed that transient and intermittent faults outnumber permanent faults, it is important to state the fault duration assumption of a self-healing approach to understand what situations it addresses. Fault manifestation. In fault manifestation, there is the severity of how it affects the system in the absence of a self-healing response. Some faults cause immediate system crashes, but many faults cause less catastrophic consequences, such as system slowdown due to excessive CPU loads, thrashing due to memory hierarchy overloads, resource leakage, file system overflow, and so on. Granularity. The granularity of a failure is the size of the component that is compromised by that fault. A fault can cause the failure of a software module, a task, an entire CPU's computational set, or an entire computing site. Different self-healing mechanisms are probably appropriate depending on the granularity of the failures and hence the granularity of recovery actions. Fault profile expectations. The source of the fault is the profile of fault occurrences that is expected. Faults considered for self-healing might be only expected faults, faults considered likely based on design analysis, or faults that are unexpected. Additionally, faults might be random and independent, might be correlated in space or time, or might even be intentional due to malicious intent. System response. The first step in responding to a fault is, in most cases, actually detecting the fault. Beyond that, there are various ways to degrade system operation as well as attempt recovery from or compensation for a fault. Each application domain has extra functional aspects that are important, such as reliability, safety, or security. These extra functional concerns influence desired system responses. Fault detection. Fault detection can be performed internally by a component, by comparing replicated components, by peer-to-peer checking, and by supervisory checks. The intrusiveness of fault detection can vary from non-intrusive testing of results, to execution of audit or check tasks, redundant execution of tasks, online self-test, and even periodic reboots for the purpose of more thorough self-tests. Degradation. The degree of degraded operation provided by a self-healing system is its resilience to damage that exceeds built-in redundancy. Self-healing systems might not restore complete functionality after a fault. Some systems must fail entirely operational. But many systems can degrade performance, shed some tasks, or perform failover to less computationally expensive degraded mode algorithms. Fault response. Once a fault has been detected, the system must select a response mechanism. Online responses include masking a fault, roll back to a checkpoint, roll forward with compensation, or retrying an operation using the original or alternate resources. Heavier weight responses include system architectural reconfiguration, invoking alternate versions of tasks, killing less important tasks, and requesting assistance from outside the system. The fault response might be optimized to maintain desired properties such as correctness, quality of service contracts, transactional integrity, or safety. Fault responses might also be preventative, proactive, or reactive. Recovery. Recovery involves issues such as integrating newly committed resources into ongoing processes, warming up resources by transferring system state into them, or acting to bring the system to a clean known state before proceeding with operations. After a system has detected a fault, potentially degraded, and invoked a fault response, it must recover operation to complete the self-healing process. A component might be hot swapped, require a warm system reboot, or require a cold system reboot to finish recovery. System completeness. Real systems are seldom complete in every sense. Self-healing approaches must be able to deal with the reality of limits to knowledge, incomplete specifications, and incomplete designs. Architectural completeness. Few system architectures are completely elaborated when the first implementation is built. Architectures and implementations evolve over time. Many systems are open in that third-party components can be added during or after system deployment. Some systems are designed using pre-built components that have details and behavior so opaque to the overall system designer that the architecture might as well be considered incomplete. Designer knowledge. Designers in the typical case do not have complete knowledge of the systems they design. Any system is designed using a set of abstractions about underlying components. A vital aspect of designer knowledge is how well the fault model for the system is characterized and whether field information about faults is fed back to the system designer. It is common for designers to have a thorough understanding of typical system behaviors, but to have little or no understanding of system behaviors, especially system behaviors in the presence of faults. System self-knowledge. Systems must have some level of knowledge about themselves and their environment in order to provide self-healing. It is limited by the aspects of knowledge built into a component, the accessibility of knowledge about one component to another component, and defects in representation of such knowledge either due to initial design defects or staleness caused by system evolution. System evolution. Self-healing systems deal with the fact that they change over time. Sources of change include designed operating mode changes, accumulated component and resource faults, adaptations to external environments, component evolution, and changes in system usage. Making use of available information on system dynamics might help with self-healing, such as being able to count on a scheduled system outage to perform healing. Design context. There are several other factors that influence the scope of self-healing capabilities that could be considered to form the design context of the system. Component homogeneity. The heterogeneity of a system tends to limit its ability to simply migrate computational tasks as a self-healing strategy and requires that self-healing approaches deal with the issue of configuration management of systems both before and after healing. It consists of exact component duplicates, or components that are plug compatible even though they have differing implementations. Some systems are inherently heterogeneous, such as the computational components within embedded systems such as automobiles. System linearity. System linearity and component coupling can greatly affect the ability of a system to self-heal. If a system is completely linear, then self-healing of one component can be carried out without concern for its effect upon other components. While many well-architected systems have good linearity, component interaction is a typical situation that must be addressed by self-healing approaches. Abstraction level. Systems can attempt to perform various forms of self-healing to application software, middleware mechanisms, operating systems, or hardware. Self-healing techniques can be applied to implementations or architectural components. It is able to give evaluation for its current status or after enhancement has been done to the system. User involvement in healing. The goal of much thinking about self-healing systems is to achieve complete autonomy. This might be an overambitious goal. Most systems have a limit to healing ability, beyond which users must become involved in system repair. The opportunity for self-healing system collaborations with users are twofold. Users can adapt their behavior to help systems function despite failures, and users can provide advice to systems to guide aspects of their self-healing behavior. Application level. Application level healing is the ability of an application, or a service, to heal itself internally. This depends on a programming language and design patterns. We are used to capturing problems through exceptions and, in most cases, logging them for further examination. When such an exception occurs, we tend to ignore it and move on, as if nothing happened, hoping for the best in the future. In other cases, we tend to stop the application if an exception of certain type occurs. For example, if the connection is not established when the application starts, we often stop the whole process. If we are a bit more experienced, we might try to repeat the attempt to connect to the database. System level. System-level healing can be generalized and be applied to all services and applications, independently from their internals. This is the type of self-healing that we can design on the level of the whole system. There are many things that can happen at the system level. The two most commonly monitored aspects are failures of processes and response time. If a process fails, we need to redeploy the service, or restart the process. On the other hand, if the response time is not adequate, we need to scale, or descale, depending whether we reached upper or lower response time limits. Time to live. The system that receives TTL signals keeps track of the last known reported state for a given TTL. If that state is not updated within a predefined period, the monitoring system assumes that the service failed and needs to be restored to its designed state. It checks expect to service, or an application, to periodically confirm that it is operational. For example, a healthy service could send an HTTP request announcing that it is alive. If the process the service is running in fails, it will be incapable to send the request, TTLs will expire, and reactive measures will be executed. Pinging. Pinging refers to check the state of an application, or a service, externally. The monitoring system ping each service periodically and, if no response is received, or the content of the response is not adequate, execute healing measures. It is a preferable way of checking the status of individual parts of the system. It removes repetition, coupling, and complications that occur while implementing the services. It is done with a script, or any other method that validates the state of the service. Hardware level. Healing on this level truly means is redeployment of services from an unhealthy to one of the healthy nodes. As with the system level, we need to periodically check the status of different hardware components, and act accordingly. Most healing caused due to hardware level will happen at the system level. If hardware is not working correctly, chances are that the service will fail, and thus be fixed by system level healing. It is a process that will automatically heal failed memory, repair broken hard disk, fix malfunctioning CPU, and so on. Reactive healing. Most of the organizations that implemented some kind of self-healing systems focused on reactive healing. After a failure is detected, the system reacts and restores itself to the design state. A service process is dead, ping returns the code 404, not found, corrective actions are taken, and the service is operational again. This works no matter whether service failed because its process failed, or the whole node stopped being operational. This is the most important type of healing and, at the same time, the easiest one to implement. For example, the whole data center might lose power, thus stopping all nodes. It's all about evaluating risks against costs of preventing those risks. Sometimes, it is worthwhile to have two data centers in different locations, and in other cases it's not. Preventive healing. The idea behind preventive healing is to predict the problems we might have in the future, and act in a way that those problems are avoided. It becomes much more reliable but, at the same time, much more complicated to implement. Information needs to be stored somewhere and, often complex, algorithms need to be employed to evaluate tendencies, and make conclusions. For example, if one of the HTTP requests we are using to check the health of a service responded in more than 500 milliseconds, we might want to scale that service. We can even do the opposite. Illustrative example. These are some of companies offering solutions and offerings for self-healing system. ABB Limited, G&W Electric Company, IBM, Oracle Corporation, SNC Electric Company, Schneider Electric, Sentient Energy, Incorporated, Siemens,